Regression. In a regression, we would like to write the numerical output, called a dependent variable, as a function of the input, called the independent variable. We assume that the numerical output is the sum of a deterministic function of the input and the random noise. That is, r is equals to f of x plus epsilon, where f of x is the unknown function, which we would like to approximate by our estimator g of x conditioning on theta, defined up to a set of parameters theta. If we assume that epsilon is zero mean Gaussian with the constant variances rho square, namely epsilon is approximated by n of 0 rho square, and placing our estimator g dot in place of the unknown function f dot, we have from figure 4.4 that the probability of r conditioning on x is approximated by the normal distribution or Gaussian distributions of the parameters g of x conditioning on theta and also rho square. We again use maximum likelihood to learn the parameters theta. The pairs x to the t, r to the t in the training set are drawn from an unknown joint probability density p of xr, which we can write as p of xr is equals to p of r conditional on x times p of x. P of r conditional on x is the probability of the output given the input, and p of x is the input density. Given an IID sample x, which is equals to the set of x to the t, y to the t, such kind of tuple, where t is taken among starting from 1 to n, the log likelihood is L of theta conditioning on x, which is equals to log of the pi of p of x to the t, r to the t, where t is starting from 1 to n. If we tear these two terms into two parts, there will be log of pi of p of r to the t conditioning on x to the t, where t is index starting from 1 to capital N, plus log of pi of p of x to the t, where t starting from 1 to n. Now we can ignore the second term since it does not depend on our estimator, and we have L of theta conditioning on x is equals to log of the following terms: pi of 1 over square root of 2 pi times rho times exponentials of minus of r to the t minus g of x to the t conditioning on theta, then to the square, then divided by 2 times rho square, which is equals to log of 1 over square root of 2 pi times rho, then to the n, then times the exponentials of minus 1 over 2 rho square times the summations of r to the t minus g of x to the t conditioning on theta, then to the square, where the summation summing with index t starting from 1 to n, and which is equals to, if we expanded the exponent instead of the log function, there will be minus n times log of the square root of 2 pi times rho, then minus 1 of 2 times rho square times the summations of r to the t minus g of x to the t conditioning on theta, then to the square, where the summation is taken among all the possible t starting from 1 to capital N. The first term is independent of the parameters theta, and it can be dropped, and can the factor 1 over rho square. Maximizing this is equivalent to minimizing the expectations of theta conditioning on x, which is equals to 1/2 times the summations of r to the t minus g of x to the t conditioning on theta, then to the square, summing with index t starting from 1 to capital N, which is the most frequently used error function, and theta that minimize it are called the least squares estimates. This is a transformation frequently done in statistics when the likelihood 1 or L contains exponents instead of maximizing L. We define an error function E, which is equals to minus times log of L, and minimize it. In linear regression, we have a linear model g of x to the t conditioning on w1, w0, which is equals to w1 times x to the t plus w0, and taking the derivative of the sum of squared arrows, equation 4.32, and with respect to w1 and w0, we have two equations in two unknowns. The summations of r to the t summing for index t is equals to n times w0 plus w1 times the summations of x to the t summing for index t. And the summations of r to the t times x to the t summing for index t is equals to w0 times the summations of x to xt summing for index t plus w1 times the summations of x to the t then to the square summing for index t, which can be written in vector matrix form as AW equals to Y, where A is equals to the following 2x2 matrix, and the summations of x to the t summing for index t, the summations of x to the t summing for index t, and the fourth term is the summations of x to the t to the square summing for index t. W is the following 2x1 matrix vector, W0, W1, and Y is the following 2x1. The summations of r to the t summing for index t, and the summations of r to the t times x to the t summing for index t. Okay, now we know A, W, and Y, where A is a 2x2 matrix, W is 2x1, and Y is 2x1, and can be solved as W is equals to A inverse times Y. In the general case of a polynomial regression, the model is a polynomial in x of order k. That is g of x to the transpose, conditioning on wk, wk minus 1, and so on until w2, w1, w0, which is equal to wk of x to the t, then to the k, plus wk minus 1 of x to the t, then to the k minus 1, and so on, until we add to the following last three terms. That is w2 of x to the t to the square plus w1 times x to the t plus w0. The model is still linear with respect to the parameters, and taking the derivatives, we get k plus 1 equations in a k plus 1 unknowns, which can be rewritten. In vector matrix form AW equals to Y, where we have A is equals to the following. Now we have a bigger one, n by n, capital N. Now we describe the first row. Capital N, the summations of x to the t summing for index t, the summations of x to the t to the square summing for index t, and so on, until the last element of the first row is the summations of x to the t to the k summing for index t. What's the second row? The second row is the first element is the summations of x to the t conditioning on O index t. The second one, we just shift the third element of the first row. That is the summations of x to the t to the square summing for index t, and so on until the last term. The last term is the summations of x to the t to the k plus 1 summing for index term t. Now, what's the content of the last row? The last row is starting with the summations of x to the t to the k summing for index t, and the summations of x to the t to the k plus 1 summing for index t, and the summations of x to the t to the k plus 2, and so on summing for index t, and until we reach the last row and the last column of this matrix. That is the summations of x to the t to the 2k summing for index t. Now, for W is equals to the k by 1 vector, W0, W1, W2, and so on until Wk. Y is also a k by 1 vector, where the first element is the summations of r to the t summing for index t. All the elements have summations of index t, but what about the terms inside of each different rows? The second row is r to the t times x to the t. The third row is r to the t times x to the t to the square, and so on, until the last row is r to the t times x to the t to the k. Okay, now we have A, we have W, we have Y. We can also rewrite A equals to D transpose times D, and Y equals to D transpose times R, where D is equals to the following form: 1, x to the 1, x to the 1 to the 2, x to the 1 to the 3, and so on to x1, x to the 1 to the k. This is the first row. The second row is 1, x to the 2, x to the 2 to the 2, x to the 2 to the 4, and so on to x2 to the 2 to the 3, x2 to the 2 to the 4, and so on to x2 to the 2 to the k. The last row is 1, x to the n, x to the n to the square, x to the n to the third, and so on until x to the n to the k. Okay, now what is r? R is equals to the vector r to the 1, r to the 2, and so on to r to the n. And we can then solve for the parameters as w equals to d transpose times d, then to the inverse times d transpose times r. Assuming a Gaussian distribution, the Gaussian distributed arrow and maximizing likelihood corresponds to minimizing the sum of squared arrows. Another measure is the relative square error, RSE. The expectations of RSE is equal to the summations of r to the t minus g of x to the t conditioning on theta to the square, summing for in xt, then divided by the summations of r to the t minus r bar to the square, summing for in xt. If the expectations of RSE is close to 1, then our prediction is as good as predicting by the average. As it gets closer to 0, we have better fit. If the expectations of RSE is close to 1, this means that using a model based on input x does not work better than using the average, which could be our estimator if there were no x. If the expectation RSE is close to 0, input x helps. To check whether regression makes a good fit, a measure is the coefficient of determination, that is, r squared is equals to 1 minus the expectations of RSE. And for regression to be considered useful, we require r to the square to be close to 1. Remember that for best generalization, we should adjust the complexity of our learner model to the complexity of the data. In the polynomial regression, the complexity parameter is the order of the fitted polynomial, and therefore we need to find a way to choose the best order that minimizes the generalization error, that is, turn the complexity of the model to best fit the complexity of the function inherent in the data.